Good morning. We continue our lecture on heat treatment of steel. This is the fifth lecture on this topic, and if we try and recall what we have done so far, you will find that these are the things which have been covered. This we have covered this. We also have looked at isothermal transformation kinetics detail. Now, these are the things which are left we have not covered yet. Let us see, we will try to cover this, we will try to cover effect of alloy elements on time temperature transformation diagram and phase diagram. We have looked at continuous cooling diagram and seen that why it is necessary. TTT diagram is an isothermal diagram, and it cannot be used to predict the microstructure in material which you get in all conventional heat treatment, where you use continuous cooling. So, like annealing, normalizing or hardening. Here where the main transformation takes place, it is a function of cooling rate, and the material or the job is cooled continuously. We have also looked at tempering. We have looked at why after hardening, this comes after hardening, and why after hardening it is necessary to temper. And this is the topic which is still left, is hardenability. So, today we will concentrate primarily on these three, and this and a few points before we begin. If you can look back, these three common heat treatment procedure: annealing, normalizing and hardening. If you superimpose the cooling curve on the continuous cooling diagram, what we have drawn here is a CCT diagram, and this is for 0.8% carbon steel, which is or more specifically eutectoid steel. Now, in this case what you do, you heat the job to a temperature where it transforms into austenite. So, this is the temperature which is A1 plus around 30 to 40 degree centigrade, and you soak it for sufficient length of time to ensure that the entire steel has been converted into austenite. And after that, if you are annealing, you cool in air, which is a very slow cooling. You cool in furnace, which is a very slow cooling, whereas in normalizing you take out the job, let it cool in air. So, air cool, whereas to harden you water quench, and when you water quench, the cooling rate is very fast. So, that means to get a hardened structure, you have to ensure that your cooling rate is faster than this particular rate, which just avoids this diffusion control transformation. So, these are the line, this is the perlite transformation start line, this is the perlite decomposition. Formation of perlite is completed, nearly completed along this profile gives you the time at which perlitic transformation is complete. And we have mentioned time and again, by isothermal by continuous cooling diagram in plain carbon steel, we do not get bainite. Now, if you quench adopt another methods of quenching, say suppose you oil quench, in that case, so maybe this is the cooling curve somewhere here, and possibly and mind you, we will come later what determines the rate at which you will be able to cool a job. But nevertheless, what is important, to get hardened structure, your cooling rate must be greater than the critical cooling rate. Say suppose water quenching, and maybe if you quench in oil, you may not be able to attain that kind of a cooling rate, then you get a mixed structure which will be martensite plus fine perlite. And as you go this way, you will find the structure becomes finer and strength goes on increasing. Now, since we talked about this rate of cooling is quite important, and the rate of cooling will obviously depend on the size of the job. If the job is large, even if you quench in water, so maybe the surface will cool very fast, but the center may not follow the same rate of cooling. So, what means is during the process of cooling, you will have a thermal gradient, and the magnitude of this thermal gradient will be a function of the rate at which you are able to extract heat, and also it will depend on conductivity of the material, which we can say, if we say that this is same, I mean this does not change much with the composition, then primarily it will be the dimension of the job that will control the temperature difference between the surface and core at any time. So, let us look at it a little more detail, and then we will appreciate why that which was mentioned earlier, say origin of residual stresses, and say suppose you are cooling in air. So, in that case you are cooling in furnace where you expect, so this is a job, and the dimension of the job will determine the rate of cooling at the surface. At the surface the cooling rate will be faster. So, this is the surface cooling rate, this is the center cooling rate at the core. So, here at any instant, say at any instant, this magnitude, this delta T in furnace cooling is very small. So, therefore, when it cools, two things happen. See, one, there will be thermal contraction, and when this transformation of takes place from austenite to the decomposition product, whether it is ferrite plus cementite or it is martensite, the material will try to expand, and the two are in opposite direction. One is trying to contract, I mean thermal cooling as a result of coefficient of expansion. As the temperature goes down, job will try to I mean become smaller. There will be thermal contraction, and as against that, when transformation takes place in the material, it will try to expand. And if one uses this judiciously, one can get a job with minimum amount of residual stress or distortion. Now, look at it, what happens if you are quenching in water. Say if you quench in water, this is the surface temperature, that is cooling rate, this is the center. And here you look at say at any time, this is the temperature difference. So, here when this has undergone contraction, this has not, core has not contracted that much. So, there will be some stress, this has undergone much more contraction than the core. So, therefore, you can imagine that surface is trying to contract, and here the thermal expansion, I mean that contraction is not that much. So, therefore, this will be subjected to compressive stress. So, the core it can elongate also in this direction. So, therefore, this will lead to distortion, and mind you, at a higher temperature strength of the material is also low. So, here this material will deform at lower stress, here to deform it, since it is cooler, you will need higher stress. So, therefore, the outside is stronger, core is softer. So, when you are cooling, this kind of transformation takes place. So, there will be some deformation because of the temperature difference and this due to this temperature difference there is a difference in the level of or magnitude of the material property, that is yield stresses are different. So, therefore, and one can say that delta T, this will increase with the cooling rate. Look at here, this is the temperature difference at any instant between the core and the surface, whereas here you see this is the temperature which is much larger and it increases here, this is much larger. So, this here this job will be much more susceptible to residual stress as well as distortion. And you can easily see, if we assume that transformation stress is much more critical, you will be able to show easily that here the job is here when this transformation Martensite starts. So, here it has already the transformation has started, and as you cool down here still the center, the temperature is much higher than the MS temperature. So, here the transformation has not started yet. So, what will happen, and here its strength is lower. So, when it is trying to expand, this will it will subject it to a stress. So, it will be subjected to a stress and it will deform also. And towards the end what happens, let us come towards the end, where here the permanent, this has by that time it has reached the temperature difference, and in fact towards the end we should actually, this curve is it is a constant cooling rate part, but when the temperature comes down it will also follow this kind of a plot. So, towards the end you will find again the temperature becomes same will be true in all these cases. So, say towards this end the temperature, this plot actually should come down and go like this. So, again the temperature difference decreases. So, that means what happens here, this will towards the end of the transformation, well this tries to expand, this has already reached its final size and it will not allow it to expand. So, therefore, here you will have compressive stress, here the tangential, there will be compressive stress, tangential, whereas here there will be tensile stress. So, this is susceptible to cracking, you can say. So, here you will have tensile stress on the surface. So, it can lead to surface cracking, and also as we have seen during the transformation, when it is trying to contract, I mean initially it will try to contract and then later on it will try to expand. So, in the process sometime you may find, if you are able to pick a capture the picture or transformation which is taking place, you will find the dimension and this direction also will change, and it can deform or it can contract depending on the nature of stresses it is subjected to. And if your job size is more, then also say suppose if it is a much bigger and you want to cool it, in that case this temperature difference can be much more. So, therefore, these are the two important things. To control the residual stresses, you have to play with the cooling rate depending on your job size and geometry, so that the material job which you are giving subjecting it to heat treatment does not undergo any distortion as well as does not develop residual stresses. Now, what are the ways of avoiding? Are there certain heat treatment procedure where you can avoid origin of such stresses? Now, if you look at the transformation diagram, TTT diagram, there are some special types of heat treatment which can be given to jobs of a particular size, and one is such isothermal heat treatment procedure is known as austempering. This is an isothermal heat treatment procedure. If you look at the TTT diagram for a particular, this is a hypoeutectoid steel. hypoeutectoid steel. You heat it to A3 plus around 30 to 40 degree centigrade, austenize, and then you cool it to a bath which is maintained above MS. And here you see the transformation at this stage is very slow, rather slow, much slower than over here. And if you can maintain it, maintain the job at this temperature, here say suppose this is the rate at which the surface is cooled. Similarly, the rate at which core will cool is something like this, and when you hold it during this time, both the temperature may become uniform also and allow the transformation to be completed at this temperature, and then you quench. So, the structure that you will get under this condition is a lower benitic structure, which has a quite high hardness. This hardness matches with the hardness that you can get under after hardening and tempering. So, look at this process here. If you follow this kind of a procedure, you are able to control the temperature difference between this core and the surface to some extent, that you can minimize the residual stress that will develop during the transformation process. And also this kind of, by giving this kind of treatment, it is also possible to get benite in a plain carbon steel, which is not possible. You can't get benitic structure by continuous cooling. So, that means a low cost material, if you can give this kind of a heat treatment, its properties are excellent, and in fact, this lower benite in certain cases has better combination of strength and ductility than martensite of similar hardness. So, therefore, this is a quite attractive proposition therefore, but what is the limitation? One limitation is in benite, you cannot get the hardness of the order of, let us say, RC as around 60, which is needed for cutting tools. So, the hardness cannot be matched. So, for that kind of application it may not be suitable. A second is, you may not be able to get this completely this lower benitic structure in the job if the job dimension is large, because in that case you may not be able to, core may not cool. So, core if the job is large, possibly you will find when your surface is cooled and brought here, but here you may get some amount of fine paralites in the core. So, that means another limitation is this treatment can be given only to thin sections. Now, another isothermal treatment process that one can visualize from this is what happens, that if you let the temperature to become uniform when you hold the job at just a temperature which is little above MS, and so that the temperature at the surface and the core becomes equal, which is shown over here. You cool here and then after that you quench it. So, in this particular case, what you are getting? You are getting hardness of martensite. You get a full martensitic structure even in this case of a hypoeutectoid steel. Now, second thing, you are able to minimize residual stress. You are also minimizing distortion also, because you are allowing, because that expansion is quite sizable. When this transformation takes place from here, this is an athermal transformation over a degree of say maybe 150 or 200 degree centigrade or 100 to 200 degree centigrade, you have 100% martensitic transformation taking place over this temperature range, and here this is athermal transformation. And so, therefore, and when 100% transformation means around 4% expansion, nearly roughly around 4%, which is quite sizable. and this will certainly lead to residual stress, distortion, and if the stresses are higher than the fracture stress or the stress necessary to initiate a crack, the job may fail, it may develop surface crack. So, what happens here in this particular treatment, you give a longer hold in Benedict Bay, and by holding this you are minimizing thermal gradient, therefore, you are overcoming this stress related problems. So, this temperature is known as Mar tempering, or sometimes it is also known as Mar quenching. So, instead of tempering you call it quenching, Mar quenching. So, if you look at the microstructure of that product, what it will look? It will be made up of untempered martensite, and untempered martensite we have mentioned it is difficult to etch. So, therefore, it will that final product should be single phase, it is white, it is untempered, and it is difficult to etch. And but after that one appears that you combine the term with a tempering, it looks that if you do not have residual stress you do not need to temper, which is not always true. Maybe if it is a low carbon steel, you may forego that, tempering may not be necessary, but if it is a carbon content is high, there is a possibility that there will be some retained austenite left in the material, and so the structure will be unstable, dimensionally unstable. It may transform during service, which may lead to change in dimensions. So, there are particularly in rather high carbon steels, it will be advisable after Mar tempering some amount of tempering may be necessary. Now, in all this heat treatment process, one of the crucial step is how do you austenize the material, and do you need to control the process of austenitization. Now, let us look at it little critically. The way that process of austenitization is also an isothermal treatment. If you recollect that phase diagram, that relevant portion of that iron carbon phase diagram, and let us consider this eutectoid steel. If you heat it, your austenizing temperature is here, 30 to 40 degrees centigrade above this lower critical temperature. Now, here if you keep it, what will happen? Here also you can visualize a similar time temperature transformation diagram we talked about during cooling. So, this is the time, this is the temperature, you have heated it, at short time you have put over here. So, even now although you have heated it, transformation does not begin immediately, because this conversion of perlite to austenite will be a time dependent process, because it needs diffusion. You have to allow sufficient time for diffusion. What will happen is, if you have a perlite is made up of, let us say, these cementite plates in a ferritic matrix. So, you will what we will have is certainly a nucleus of austenite will develop over here, and this will try and grow. Similarly, this will develop at several places it will develop, and they will try to grow, something like this. So, this is a time dependent. So, for certain period of time you have to allow, maybe this is the time where this transformation starts. So, you can say this is AS, say maybe here around 0.5% austenite has formed in the structure, and with time it will go on increasing, and this you can say here nearly austenite will be nearly 90% or 99% austenite is over here. But even when you have all these austenite grow, so these are which is pictorially shown. So, similarly this austenite will grow at many other places, and finally what you will have. So, this is say prior austenite grain size. What will happen, that that austenite grains which will form, they will be finer than, to start with it will be finer. You can get a very fine austenite grains. But it is not enough to convert this, you have to see that this austenite is homogeneous. For that you have to allow time. So, over here even after all ferrite is gone, you may still be left with some of the places there will be some amount of cementite particles undissolved. So, which you have to allow still times for these to dissolve in austenite, and maybe this is where that dissolution is complete. But after this dissolution is complete within that austenite grain, carbon concentration may be different, because whenever there is a, suppose just before this process of dissolution is complete, there was a cementite particle here. So, what happens, the carbon concentration surface is more, core is less, you have to allow time for this composition to become uniform. So, which is shown over here, and once this becomes uniform, now there is no carbide to or particles to control its growth. So, after some time this austenite grain will start growing, and it may become, if you keep it very long, it will become coarse. And as we will see later, that is, it is a coarse grain structure is not desirable, because coarse grain structure they have a poor toughness. So, one likes to avoid it. And see, if you try and if you have to avoid, so therefore, what is more important is to optimize the condition. So, maybe, so this is why you will see, say maybe you will say 30 to 40 degree centigrade you will keep above this. So, which may be say somewhere here, and maybe this time you have to allow. So, maybe just over here before this grain coarsening start, you have to stop that soaking, so that you get fine. A process of austenitization aim is to get fine homogeneous austenite, and once, and this process will be exactly same irrespective of the composition of the steel. Only difference that may come up is the temperature of austenitization may differ, and like hypoeutectoid steel, this is the temperature, and here again the similar transformation diagram one can visualize. So, this will be the start, beginning of formation of austenitic grain, and similarly this is where austenite starts to become very coarse. So, therefore, a similar diagram one can think of in case of hypoeutectoid steel as well. Now, let us try and understand, we mentioned about a term called hardenability. What does it mean? So, we just mentioned that when you quench a job, so this is a job, even if you quench in water, it is the surface which will cool very fast, because surface you will cool very fast, but point is when you quench it in, imagine this has a temperature around, say if it is say 760 degree centigrade, if you are cooling from, you dip it in cold water, suddenly a blanket of steam will form. Now, blanket of steam is actually not a good conductor of heat. So, it will immediately there may be a I mean all this, you have to somehow break this film, then only. So, that means if it breaks, then some bubbles will form which will come up. So, it will start possibly from the bottom portion, and as this steam blanket disappears. So, this is the place where you will have the maximum heat transfer rate. So, therefore, you have to try to promote that kind of a heat transfer. So, that means you have to you do not allow steam blanket to form. So, by this it is possible to cool a job. I mean we just deviated a bit, but what it is important is, no doubt it is possible to get a very high rate of cooling at this, but if the job is large, you will find that center will cool much slower, because here the heat will be transferred by conduction only. Here is a conduction, but outside you can play with it, you can agitate, you can allow this bubble to form, and by violent agitation you can cool this surface quite rapidly. And if you plot the cooling rate, you may find that here the surface is possibly cooling like this, whereas the core is cooling like this. So, core you will get a structure made up of fine pearlite, surface you will get martensite. So, you have surface hard, core is soft. So, that means there is a, if you plot this hardness along this direction, if you try and plot the hardness, what you will find, this is the job. So, surface you have high hardness, so maybe it is 64, but as you go to the center the hardness drops. This curve, if it is cylinder, it should be symmetric, let us say. And so, what you have here, you have fine pearlite, here you have 100% martensite. In between you can think about a structure where it is 50% martensite, 50% pearlite. And if you after quenching, if you take a section, develop the microstructure, this demarcation is very easy, because martensite is difficult to etch. So, what you will find, then this is the job, the center portion will etch. So, this will become dark, this is bright. So, what you can do, you can measure, say suppose you can measure this diameter, you can measure the zone, diameter of the zone in which you have parlitic structure or soft structure. So, in this outer periphery, this annular region, which is d minus d, here you have the maximum hardness. Now, hardenability determines the ability of a material to harden. We will later come to it, what are the factors that determines hardenability, but let us first look at how we can get a more quantitative definition of hardenability. It is not hardness. So, in this particular case, the job has a very high hardness at this surface, but this depth of hardness is this. If you want to get fully hardened structure up to this, then how will you proceed? Now, if you can do a very simple experiment, take the cylindrical test pieces of different diameter, heat them all in the austenitic range, and then you quench. And let us say we use cold water as the quenching medium, cold water with agitation, and if you quench, and now let us see each after you have quenched, you cut these samples at the center and you try and polish and look at the microstructure or the macrostructure. You will find, say suppose here, so this is a little larger diameter, here you find that this is the portion where it is pearlitic structure, ferrite pearlite. If the job becomes smaller, you will find this is the size. If you make it still smaller, this. So, in this way you can attempt to find out the diameter where this disappears. This is a non-exit, this doesn't, this just disappears. So, this is the best way to think about it, is when you take a section, you can measure this hardness from this end to that end. This is the hardness profile, this is let us say this is hardness 64 at the surface, and 50 this martensite hardness of this mixture, 50% pearlite, 50% martensite. This is around RC 54 for eutectoid kind of steel. So, around carbon content around 0.7, 0.8, this hardness of 50% martensite, 50% pearlite will be around this. So, look at where you have, then you say this is my depth of hardness, this is the depth of hardness, whereas this is diameter. If you measure, this is the dimension or the core dimension of the core region which you have not been able to harden. So, one way of defining this hardenability I mean this is a measure or gives an idea up to what depth one gets this particular hardness. Or you can say this depth is an indicator of the ability, depth of hardness is an indicator of the ability of the steel to respond to hardening, and this also one you can say may be one of the definition of hardenability. Now, let us try to have a little more quantitative definition. If you plot this diameter, say if you have measured this diameter, you make a plot this diameter against the diameter of the job. So, you get say different points here, you have a large number and then try to extend it to a region, finally you find this is the dimension where this d is 0. So, what it means with this quenching procedure, you in a particular material which you have taken, the steel you have taken, if this diameter is less than this critical diameter, then you will be able to harden it through and through. So, that means what it says in this particular diameter you will have surface fully martensite, 100% martensite, and in the center you will have 50% martensite, 50% perlite, and for all practical purposes one takes this as the fully hardened structure. And now obviously the reason that comes up is what is the what are the factors that determines this diameter, this critical diameter. Obviously one is the quenching medium that you are using, that cooling rate. So, if you are doing say quenching in water quench maybe it is still a water, no agitation, you will have one value, and once you have, and when you quench in water plus agitation, if you agitate vigorous agitation, then you will find that this critical diameter will be higher. So, this is not a, you cannot say that this is a some kind of a material property, it depends also on the composition of the steel, say particularly the carbon content, and as we will see later it also depends on the presence of other alloying elements. So, it depends on the composition of the steel, it also depends on the austenite grain size. Why should it depend on austenite grain size? We will look at it more critically later. So, if you have a large grains of austenite, then you can see that to harden you have to suppress diffusion control transformation. If you have a coarse austenite grain, the site where perlite nodules can form, they are limited, they can form only here. So, here only here perlite nodule can form. So, whereas if you have a fine perlite, here the number of places, the frequency of the sites are much more. Number of sites at which this transformation can take place is much more in fine austenite, whereas in coarse austenite this is much less. So, therefore, diffusion control transformation here will be slow. So, this is also an important factor that will determine this critical diameter. But critical diameter is still it depends on the cooling rate. Now, the question comes, can we have a term which is independent of cooling rate? So, this is the first attempt to define a proper quantitative definition was given by Grossman. What is thought is or he visualized a quenching medium which is an ideal quenching medium. And what is an ideal quenching medium? When you quench the that job in water, say from 760 in cool water. So, you are decreasing the surface temperature drastically. Now, if you think of an ideal medium where when you quench the surface temperature comes down immediately to let us say room temperature. this surface temperature immediately comes to room temperature or 0 degree centigrade, let us say, immediately comes to the temperature where transformation is complete, below MF temperature. In that case, what is happening? Now the heat transfer is totally determined by two things. Is one is this conductivity, it is but for this you have to have a very infinite convective heat transfer coefficient, because the major mechanism of cooling here will be convection over here and the water, conduction within the job. So, what we can think about that a quenching severity parameter defined as H, and this we take it as a ratio of the heat transfer coefficient, that convective heat transfer coefficient H, and this is the conductivity of the job. So, H by twice K is defined as a quenching severity. Say still water, you define, say maybe you define that still water quench, normally you take H as 1, whereas ideal medium, this is ideal quenching, this is infinity. What does infinity means? That means heat extraction rate by convection is infinite, it is very large, much larger than this case. So, this is an hypothetical quenching medium. And then you can define, people can do some measurement, actual experiment measurement, and they have tried to find out, like this brine quench, if you put some salt in water, then the quenching rate becomes much faster. So, brine quench with agitation has the quenching severity 5, whereas if you have oil quench with agitation, we will have this. Maybe oil quench without agitation will be much less severe, maybe 0.2. So, this is how it is possible to define. Grossman introduced the concept of quenching severity, but there are a lot of later development. If you have time, we will look at that, but a little later. As the most important factor, therefore, is to convert this ideal, this is critical diameter which you have measured for a particular quenching medium, how to convert into a parameter which is independent of cooling rate. So, what he did is, if you define this is another diameter, that is critical diameter when you quench the job in an ideal quenching medium d I. So, this is called ideal critical diameter, ideal critical diameter, ideal critical diameter is defined, and the relationship between dC and di. So, therefore, if you can draw such lines, these have been evaluated experimentally, that ideal quenching medium has infinite quenching severity. So, this is this, whereas, so here this is the 45-degree line. As the quenching severity decreases, so H decreasing, so H is increasing in this direction. So, as the quenching severity decreases, you will find that if you have found out this critical diameter by, say, let us say by water quenching here, then you can say that an ideal critical diameter will be higher than dC. So, in all cases you will find that this is, therefore, ideal critical diameter is a dimension of the job, is the maximum dimension of the job. If it is quenched from the proper austenizing temperature, then it will harden through and through. That means, it will have the 50% martensite, 50% perlite at the center, and 100% martensite at the surface. So, this is a definition of hardenability. One can say ideal critical diameter is a good definition for hardenability. Now, the question that comes up is this procedure of determining hardenability is quite tedious. You need a large number of samples, they have to be quenched, they have to be cut, and you have to prepare the microstructure. It is a very time consuming process. So, can there be a method by which you can determine hardenability of a steel quickly? Because unless you determine this hardenability, it is very difficult to design your heat treatment procedure, that quenching sequence, the rate at which you will cool. And let us see one such method of determining this hardness by a single specimen. This is called a Jomini end quench test. So, we talked about austenite grain size measurement in one of the earlier lecture, where if you can give a gradient quenching. So, what you do, you have a job here, there is a part which you can either screw, thread it. So, this is your job. There is a provision to fix it on a cooling fixture. So, this is or this can be a single part also, or sometime you can have a collar, you give a collar here which can be put on a rig. So, so main part is this, and the diameter is around of this is around 25 millimeter, around an inch in diameter. So, maybe 2.5 inch to 2.5 inch long, depending on that hardenability that you expect. Now, what you do, you heat this entire job to the proper austenizing temperature, and after it has been austenitized, you take it out, put it on a rig in this support, and then try to cool this edge by spraying water. Cold water you keep spraying. So, when you spray, it comes out, the water comes in the water goes in this direction and comes out in the form of an umbrella kind of thing. It comes out and forms. So, by this what you are doing, you are having the highest cooling rate here, lowest cooling rate at this end. So, what you have is a gradient cooling, and then what you do after it has been cooled to room temperature, take out the sample and you polish, grind a small portion here, the center. This is a cylindrical piece. Now, what you do, you place this in a Rockwell hardness testing machine. So, there are normally this, so you can put it on a Rockwell hardness testing machine, and you have indenter, and there are also devices you start measuring this hardness, maybe. So, this is the quenched end, you start measuring hardness from this end at some regular interval, and all these were done, many of these equipments which are you use, there are thing where you can move it, that there are stage which can be mounted on the Rockwell hardness testing machine, and by rotating one cycle you can move the job by a fixed distance, and usually this depth is maybe 1/16 of an inch or 1/8 of an inch. You keep moving, and then you get hardness from the quenched end to the other end, and then you make a plot. If you make a plot, you will find you get a plot like this. Then you can say and look at that place where you get hardness 54. Then you can say this is the depth of hardness in a Jomini end quench test, and once you get this, there are now experimentally determined conversion charts which are available. So, one such graph is here, and what you do, look at this is a graph, this is the Jomini depth, hardness depth, this is Jomini hardness depth which you have measured, and look up this chart, and this chart will give you, this is the ideal critical diameter. So, therefore, what we do here, so here is a method by which you can determine hardness in a very by performing test on a single specimen. So, compared to the Grossman method, where you need multiple specimen, here you need single specimen, and what you are using? You are using gradient quenching method, gradient quenching. And now, a point about the factors that determine hardenability of a steel. What are the factors? We just mentioned that one important factor is the austenite grain size, and so let us see what are these factors and how do you determine them. So, one way is this austenite grain size. I think this method of determining austenite grain size was talked about earlier. Even it is possible that Jomini end quench test, after you have measured the hardness, if you try develop this phase develop microstructure. If you look at that microstructure, there is some place you will find there are these austenite these pearlite nodules which are existing around prior austenite grain size. So, here this portion is martensite. So, this will happen, say if the Jomini end quench, the depth of this is the quench end. So, somewhere here this is 50% martensite. So, here it will be very difficult to find out prior austenite grain size, but somewhere here you may find out a microstructure where you will get say it's these are the marked prior austenite grain size will be marked by these pearlitic nodules of pearlite. And we have just seen that if this austenite grain size is fine grain size has low hardenability. Fine austenite grain, then low hardenability. Now, another important factor we said is the composition. One of the prime composition is carbon contents. So, if you have carbon in the steel, that carbon content percentage carbon, if you increase, the hardenability increases. This is quite obvious. If you increase carbon content, we mentioned time and again that the diffusion control transformation becomes slower, that CCT diagram shifts to the right at a high temperature end. So, therefore, you will be able to get full martensitic structure with a much slower cooling. Later on we will also see that alloy addition of other alloying element also affects hardenability. So, to sum up, what you can see that this hardenability is defined in terms of ideal critical diameter. If you try to generate a plot for this this ideal critical diameter as a percentage carbon, you may be able to generate such plots, and here we have put certain numbers. These are austenite grain size is defined in terms of numbers called ASTM grain size number. And how do you define this number? This is the number of austenite grains per unit area, and this is an exponent 2 to the power n minus 1. Say suppose if n is let us say 4, this or let us say this n is 6. So, 6 minus 1. So, this will be 2 to the power 5. So, this is 32. So, 32 you will get 32 number of grain. If you look at that microstructure at 100 magnification, that in that field you will see 32 grains of austenite per square inch, And all these procedures were devised at a time where this inch actually many of these are defined in terms of inches, many of these dimensions it is possible to convert it, but that is for theoretic to maintain that SI unit. But the point is that means per unit area the certain number, this index represents number of grains per unit area. So, if you look at this over here, for a given composition, if the grain size is coarser, this ideal critical diameter increases. So, this is where it is written is a finer austenite grain size, it has lower hardenability, but we always prefer fine austenite grain. So, just to sum up here, what we have covered today is austenitization process. We looked at two important isothermal transformation isothermal heat treatment procedure, austempering, martempering. We have looked at hardenability, little details. I think what we missed this, and maybe we will consider this in the next class. Thank you very much.